Here are some exercises for you to see how your Henderson-Hasselbalch equation is used to make some computations involving buffers. So we have three items for these set of exercises. Let's start with letter A. So given that the Ka for acetic acid is 1.8 times 10 to the negative 5, let's calculate the pH for a solution containing 0.10 molar acetic acid and 0.10 molar sodium acetate. Now you have learned, if we look at these two solutions, two components of the solution, we see that we have equal concentrations for the conjugate base, which will come from sodium acetate, and the weak acid, which is acetic acid. So automatic in our Henderson-Hasselbalch equation, pH is just equal to pKa because the second term is equal to 0. So we just compute for pKa, which is again the negative logarithm of Ka. So we get the negative logarithm of 1.8 times 10 raised to negative 5, and this is equal to 4.74. So the first one is easy, especially if you understand the importance of the second term in your Henderson-Hasselbalch equation. So let's go to letter B. So let's compute for the pH of a solution containing 0.10 molar acetic acid and 0.050 molar sodium acetate. So this time we see that we have 0.10 molar of the weak acid, and don't forget, this is the salt of our conjugate base. And you know that salts dissociate completely in water. So your sodium acetate is basically dissociated into sodium ions and acetate ions. So the salt, we refer to the salt as our source of the conjugate base. Now, since this is completely dissociated, it follows that we also have 0.050 molar of our acetate. So if initially I have 10 sodium acetate and all of them dissociates, then I also get 10 sodium ions and 10 acetate ions. So in our Henderson-Hasselbalch equation, actually we know the value of pKa, which was solved in the previous item. So that's 4.74 plus logarithm of the concentration of the conjugate base, which is 0.050 molar, and this is divided by the concentration of the weak acid, which is 0.10 molar. So computing for pH, we get a value of 4.44. So let's analyze our answer. We see that we have a higher concentration of the weak acid. Therefore, we expect that we will get a slightly lower pH in reference to the pKa. Okay? So our answer makes sense because 4.44 is less than 4.74. Now let's move on to the last one. This time, the concentrations are reversed. So the solution contains 0.050 molar acetic acid and zero point 0.1 molar sodium acetate. So the ratio is now reversed, and this time we have more of the conjugate base, right? So we expect that the pH of this solution would be slightly higher than the pKa. So it should be slightly higher than 4.74. So our ratio is 0.10 molar divided by 0.050 molar. And computing for this, you will get a pH value of 5.04. If you notice, the difference is the same, right? It's zero point 0.3 units from the pKa. Now, the direction is determined whether you will have more of the conjugate base, so you will get a higher pH, or if you have more of the weak acid, so you will have a lower pH than the pKa.